Alright, so the first question is a kind map question. Alright, exactly how I go through this question is how he wants you all to do it. Alright, so just keep that in mind. Alright, so in this question here, let's hide this. Alright, so this question here, very simple, right? He gave you a 4 bits kind map. Anytime you see A, B, C, D, it's either going to be 4. Yeah, gonna be 4, because 4 is really the best way to bring it, right? What these things now, all I can my does give is ones, right? One is a minimum, right? You're looking for one. All kind of maps is you really care about is the ones. It really matter what you're doing, right? So if they give you this here, the sum A, B, C, and D, these numbers here are where we'll find the ones, right? And D means I don't care. So in position 7 and 12, you just have an X, right? And everything else will just be zeros. Yeah, that's all it is. So in this piece here, the sum here, these position numbers here, which I'll show you, you'll get 1. You just put 1 in that position, right? And in position 7 and 12, we have an X, that don't care. The X means it could either be 0 or 1. And the rest of positions that not here, just have zeros. Alright, so drawing up the table. So the table not gonna change, right? So it's a 4 by 4 table. So there's 4 by 4 because 4 bits. All right, so we have A, B, C, and D. So we have 1, 2, 3, 4. 1, 2, all right, 3, 4. All right, so if you remember when you went through it, when you're numbering it, that was very specific. We have number, and not just 1, 2, 3, 4, 5, 6 going on here. No, very specific, right? So your number is you go forward, reverse, flip, forward, reverse, forward. Reverse. So I'll show you. So you start with 0, 0, 1, then 2, 3, then 4, 5, then 6, 7, and then for 8, you have to go on the next side. 8, 9, flip, 10, 11, and you have so 7, 8, 9, 10. Oh, up to 11, I mean, wrong box. 10, 11, all right, 12, 13, and then 14, 15. Yeah, so that's how I was labeled the box for column. It doesn't matter if it's at 8, like if you give it as 8, it's the same idea. Right, you go forward, 0, 1, then flip, 2, 3, then 4, 5, 6, 7, and then when you reach 7 now, you had to flip it on the next side, and you just go to the bottom, and you go 8, 9, 10, 11, flip again, 12, 13, flip, 14, 15. Memorize this. Know how to write it down. Okay, getting real marks for this here. It's the same number, yeah? So it doesn't really change. So like if I give you something like this, we just 8, 1, 2, 3, 4, 5, 6, 7, 8. It'll be the same thing. 0, 1, 2, 3, 4, 5, 6, 7. Right? It's just now if you were to add a next 8 connected to this, the only thing I had to remember is that I'm not gonna go 8, 9. The 8, 9 gonna be here and then they're going in. Yeah, you're going in. So we'll kind of merge in the middle. Right? Just remember that to forget that because it's very important. Anyway, so nice. So we have our table. So now we could fill it in. So the ones are in 2, 4, 6, and 14. So in those boxes, so 2, 4, 6, and 14. That were 1. And the don't cares in 7 and 12. So I don't care just a X. So 7 and 12. And the rest will just have zeros. So 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Right, and aside that, you have your column up table. 12 marks. Right, so yeah, that was part. Nothing more, nothing less. Alright, so now the next thing that I want you to do is determine the minimum SOP. So Just to paint the picture period, I think so went through this process over and over. The things that you need to know is what minimum is implicant, essential prime implicants, all these things, right? All these ones here, every time you see a one, that is a minimum, yeah, or is that implicant? Yeah? No matter what order I write through it in, is that all these ones here, the x's too, if I want it to be, are implicant, right? The rules that you need to remember when you're trying to form implicants of groups, right? You could circle 2, 4, 8, 16 once, right? The second thing is it must form a square or a rectangle. As you need two things you have to remember. Yeah? So what I'm trying to say is this is not implicant, right? This cannot be implicant because it's true and it's not it is a rectangle, yes, if I also drew it like that, but it's not because it's three ones, right? So once you remember that, those two things, it cannot be, sorry, it have to be a multiple of two. So 2, 4, 8, 16. And in your case, the largest box you're going up is a 4 by 4. So the largest amount of numbers you're going to get is 8 because obviously you're not going to bring the whole table with ones. Right? So the largest you might get is 8 ones in a box. Right? You're not going to get 16 because that means the whole table is just ones. All right, so looking at this here, if you're trying to break it down into its implicants, or the prime implicants as they call it, right? All these are implicants. We put them together in boxes, you get prime implicants. From the prime implicants, the minimum amount of boxes you need to cover all the ones are the essential prime implicants. That's how it does go all the time. If you say find the minimum SOP, he just asking you to find the prime implicants, which is just circling the ones with the boxes. If you say find the essential prime implicants, you basically asking him, given the amount of boxes you have there, what is the minimum amount of boxes you need to cover all the ones? See, it's the same pattern over. It doesn't change. Right? So if I want to find the minimum sum of products, then I will SOP means, right? Say adding up the products. So like look to see how we could cover all these ones here, right? For simplicity, let go through. So you could actually just practice there. You could circle the boxes, but really and truly you're picking the iteration that give you the least amount of boxes to cover all the ones. Yeah, the more you practice this, you just get accustomed to it. Trust me. This one you can't just go in the exam and just do it. Right? You have to actually practice and see, where's the minimum amount of boxes I could use to cover all these ones. Yeah? So in this one here, what I could do, what the first thing I always do when I do these questions is think to myself, where's the biggest box I could get? So if I looking at this, the biggest box I could get, if I make this don't care one, because remember, the don't care could be a one or a zero, right? If I was to make this a one, right, I could do this. So I could combine this part with this part. Yeah, I think I showed you all the folding now when we did this topic. Yeah, you could do that. So that one box right in, covering majority of the ones, and now the only other box I need to cover, the additional one, will be this here. And just say that all the ones covered, I'm making this don't care zero because it's easier. If like try a different iteration of it. So and you'll see how it giving you more boxes, right? So if we didn't treat this zero, this x here as zero, right? So that means I could have combined this here in the corner. Yeah. So I'm treating this one here as a zero, and you could treat this one here as a zero. Yeah, that's to keep it consistent. So if we treat the both don't care as a zero, you get one here. Then you'll have a box on top here to cover that one. And then you have to draw a next box on top here to cover the next one. So in total, we use 1, 2, 3 boxes to cover it. Yeah? Let's try next iteration of it. So we'll use, let's try next iteration and see. Let's say this don't care at the bottom. This one here is 1, and we'll choose this one here to be 0. And let's see what we'll get for this one. So same idea, we could cover this fold in one here. All right. When you cover that now, We cover this one. And then we had to cover this one. And then you had to cover this one. Yeah, come on, back. I can't cover three. I had to cover two. Yeah. So that is somewhat one, two, three. That is four boxes I use. Yeah. So and then let's try the other iteration where the both don't cares are ones. So instead of this being zero, both don't cares are one. And let's say we get. So now let's see. So we could cover this again, like one box here. All right, then you have two boxes, then you have three boxes, then you have four boxes, and then you have to cover this one. Well, how about to do that? Looking at it, let me start. I could fold the four boxes. So there's two here, there's one here, and I could fold out this piece here. Yeah, so like one, right? Yeah. Now seeing it. So as I say, as you practice it, you'll tend to see those stuff more, right? And then you cover this here, and then you have to cover this here. Yeah, so like one, two, three, like three boxes. Yeah, so those iterations, you'll notice that if you had different amount of boxes, you will have time in the exam. Trust me, you'll have a lot of time in the exam, right? So you could go through the iterations and make sure that you pick any one that gives you the least. All right, so I'm going back with the one I had before. I think that one gave me like two. So I think I should this don't care as a one and this one as a zero. All right, so you have this here going with this. So like one box. And then on top here, you got one next. So like two. Yeah. So just like that, again, I'm a minimum SOP. So now that's how I write it out in a way that I could read off. So if you remember the pattern, this is 0, 0, 0, 1, 1, 1, and then 10. Same thing underneath here, 0, 0, 0, 1, 1, 1, and 10. Make sure you remember that. Make sure, I'll let you repeat it. Make sure you know how to draw up this thing with the numbers, right? Plug in the values with the, when they give you the sum, the A, B, C, D, and you don't care with the D. Make sure you know how to draw up your table. Make sure you know how to label the bits in the table with the A, B, and the C, D, like these things there. That's just the skeleton of the question. Right? The second thing, the third thing you need to know how to do after you have the ones you came up, you have to know how to get your prime implicants, which is the boxes, and then like majority of matters. And the last thing, how to like name each of the boxes, right? When you name the boxes, you're just looking at the bits on top and you're just asking yourself what the box have in common. Whatever it have in common will be the name of the box. So we have this box here, which is the first one, and we have this one here, the second one, right? So if I look at the first box here, right, what it have in common? So we had to look at the vertical, and then you had to look at the horizontal. I mean, you're looking on top here, and then here. So if you look on top, you can clearly see that zero, this row have a zero, so that B prime, and this piece here also has a B prime. Yeah, so that's looking at like that. You notice B prime common, B prime common. So we can write that down for the vertical. And the horizontal now we have D and D. Yeah, remember they're in the same horizontal row. So in the horizontal, they have the D in common because you see in one here. And the vertical now they have the B prime. Because A is now 1 because 0 here is 1. So it changes. So this B prime here and B prime here. So this will be D here. Right? And then plus there's sum of products. There's our product plus you just added these boxes together. The other box now is the two, same idea, what it have in common. In the vertical, you can clearly see that is A, B prime, because it only have one, only in one vertical line, right? So the both of them will be in it. So it'll be A, B prime. And then in the horizontal now, D not common because it change. So C prime common. So therefore that will be in the, yeah, in it. Yeah? And that is it. That's the answer. When you name in the boxes, All it is simple. Look at the box, look at the on top, the vertical, see what they have in common. How you does know? Look at the bit numbers, that's why drawing a bit table important, and see which bit didn't change. So like in the first one, you notice that they both have a zero in the B prime position. So therefore B prime will be in it. And then you look at the horizontal. In this case, they both had D because it's one and one, didn't change. So that's the first one. And the second one now, since it's in the same vertical column, therefore the two bits will be the same thing. So that would be in it. So in this case, it was A, B prime because 1 and 0. And then the horizontal, they both have a C prime term, so that'll be it. And just so that you get your minimum sum of products. And that's the answer. 12 marks. It's a nice question to practice. All right. All right. Any questions on this? Oh, you're all good. Because for sure this is going to come. I will take that as an, right? So same idea. Make sure you not to draw the table. Label the bits. It's normally the same thing. A, B, C, D. Make sure not to number the bits. 0, 0, 0, 1, 1, 1, 10. Same thing for the horizontal and the vertical. Plug in the table with the don't cares and the minimum dimension, sorry. And from there, you know, to get implicants. Nice, nice. I really want this. All right. All right, nice. So I go back. Question B. Well, 1B, right? Alright, so let's go into it. So they said in figure 1A is a completed column map with the for so there are 4 bits. Determine all the prime implicants along with the minimum cover. Okay, so this question here, as I told you, the prime implicants, all these shapes, the rectangles you see in here, all of them are your prime implicants. Yeah, remember, implicant is all the ones. So if I were to remove all the colors, all the ones in the table would be your implicants. When you group the implicants together, you get prime implicants, which is all the boxes. You're just trying to cover all the zeros and whatever order you want to do it. You're just trying to cover the zero, the ones, sorry. Once you cover all the ones, you get your prime implicants. From the prime implicants, they will ask you to get, they will say the essential prime implicants, or they just might say the minimum cover. Because the central prime implicant is the minimum amount of boxes you need to cover all the ones, which is also the minimum cover, is in itself the same thing. So never get confused. Right? They're just asking if it is essential prime implicant, which is the minimum amount of boxes, which is the minimum cover. That's all it is. Alright, so never get flustered when I ask you that. You would just state in a way that I probably never see before, but it's the same thing. So as I say, all the prime implicants that are already here for you. So you basically just asking you to name each of them. Yeah, and then you will say get the minimum cover. So from all these boxes here, you need to pick the smallest amount of boxes you need to cover all the ones. That is what the essential prime implicant or the minimum cover is. Same idea. So don't get confused. These don't get confused. All right, nice. So looking at it, so we added name all those boxes. Right, the same idea I show you, right? So I try to color code it with the colors they have. So this box here, same idea, right? So you notice this box, it fooled the corner, the ones in the corner, if you notice, right? So that box kind of fooled them, but it's the same idea, right? It will still have a vertical and a horizontal piece. So looking at the vertical, this one have a 0 and a 0. S with have a S prime term, right? The R not common. And then for the horizontal, now looking this way now, this have 0 and 0. All right, so yeah, so that would be what Q prime. Yeah, so when you fold it here, you'll get Q prime. Because this have a 0. This is 0. Yeah, so Q prime. Yeah, that's all. So that's the first one. What color I need? Green or the green? All right, so for the green now, same idea. What common in the vertical? In the vertical, this 0, 0. So same idea. So S prime will be in it. And then for the horizontal now, P prime. Because, you know, it's a 0 here, 0 here. Same idea. Nothing gonna change. All right, where's the next one? We have purple. So the purple now, I want it to be more purple. All right, so the purple, same idea. What I have in here is the vertical, everything changes. So we know for the vertical, it have nothing because it constantly cut our whole box there. And this is for literally different things. So it have nothing in the vertical. So we have to try the horizontal. In the horizontal, they both have a Q term. There's one. So therefore, this whole box here is just Q. Because it have nothing in the vertical that is the same in each, clearly changing. And the horizontal now, it doesn't have a P term because it's constantly changing, and then the units in that common is the one, which is Q. So F is equal to Q. And then one next one. Let me see if the closest thing after that color. I gotta use this again. All right, so we add this piece here. So in the vertical, well, we know it's in a vertical piece, so both of these in it, so that I will RS prime. And in the horizontal, they both have a P term. All right, so I'm not in, but we must any blue. All right, so do the blue. So the blue now, same idea. What the vertical have in common? Zeros, so zero here, so that R prime. All right, and then in the horizontal now, they both have a P term, so that PR prime. Since that is all blue, red, dark color, green. Yeah, so that's your prime. So that's looking at the name for it. All right, and from here, that's gonna get the minimum cover, card or the truth. Is the trick, right? The trick to get the central prime accounts, right? You're just looking for the boxes that have a one that isn't covered by any other box. Yeah? If you meet a box that like all the stuff covered in it, you will just pick the box that's covered in the amount of ones, the most amount of ones. What I mean by that is you look the first piece. Looking at the first piece to get the central prime implicant, which boxes have a one that isn't covered by any other boxes. We clearly see that this box have a one that is not covered by any other box. And this big box here have a one that isn't covered by any other box. So we know this one here and this one here is a central prime. As you can clearly see, like cover any real ones, right? The next amount of ones that we need to cover, because looking at it, this is what I do to my brain, right? When I do it, I'll just shade the ones that are covered, because I will have the paper and I will have the exam paper. So I shave that and I shade that. Watch how you can boil on, eh? So looking at this, we already covered all the ones. Which ones we missing right now? We missing this one here, this one here, this one here, and you could by extension say this one, but it's already covered, right? So we have two options. We have the green because we can't pick both. We can't pick the green and the red. Come we're looking for the minimum cover. Yeah, because if we pick the green, we have to pick the red. But the thing about it, if you look at it closely, the red already cover and everything I need any corners. Yeah, and obviously this here is not one because is you just remember in the outside now we have three options. Look at the option, right? I'll label the options here. We have this option one. We have the red option, that option two. And we have the green option, that option three. Man, we're looking for the minimum cover, right? So let's go through all the iterations. If I was to choose one, right? Therefore, this one here will have be covered, right? Therefore, when I choose that one now, I still need to pick another one to get the other two ones on top. Remember, this one already covered in this box here. So I don't really care for it. But if he in the box have another one, that is okay. But I still need the box that cover in the outside. So if I pick one, I will have to pick another one, either the red or the green. So like two I will have pick. So let's see if I can get another more optimized box. If I pick the green, right? The green will have covered the two on top, but it will have missed this one at the bottom. Yeah, so I'll have to pick this one and the green to cover everything. Yeah. So if I pick the red now, the red will be the best option because the red covering all the ones that are near the corners, as you can clearly see. Yeah. So the central prime implicants now are choosing the red. So now this covered, this covered, this covered, and well, this was already covered, and that is okay. Yeah. So that's why it does get the essential prime implicants. You're just breaking down the table. The three steps, first thing, You look at the boxes that have a 1 that is not covered by any other box. So clearly you could just look at the table, the purple and the blue, one time. What others do, shade it, like literally shade it, so you know you cover the ones that you already account for. It'll make it easier to break it up, right? Obviously, you could just erase it after the exam or draw over the table and you go on at the page. From there, now you're looking at the ones that you need to cover, yeah? And then from those ones, you pick any box that cover all the ones already, if you could. Yeah, if you pick one small one, you try not to pick more. We're trying to get the minimum. So you could go through the iterations. If I pick this box, I gotta pick, you could go through and you'll realize that you reach a very optimized box or covering all the ones that you need and you just choose that. You can't get the answer one time unless you practice it real plenty. Yeah, but it's the same idea. So the minimum cover, the boxes that we need is Q, because Q covering that, plus we have this R prime P, and the red one, which is Q prime S prime. So that's the minimum cover. That's the minimum amount of boxes we need to cover all the ones. All the essential prime impotence. All the same thing. Yeah, but it's the same steps. Same exact steps. Looking at the ones that are not covered by any other box, that is 100% a essential prime impotence. Then when you shade all the ones that you cover with the bigger boxes now, you might notice like this one here, and realize that you have boxes covering all the other ones, which is okay. But you pick any box that covering all those ones. Or you pick any minimum amount of boxes that you need to cover the rest of the boxes. If one box already covering all the ones, well, just to choose that one. Alright? If you really and really can't get one and two is the best you can do, those two boxes will be the essential parameter. Yeah? And I heard us do that first. Alright, any questions on that one? We all good. Alright. Alright. Okay. Alright, let's try this one. Never get flustered. Okay. So a particular digital system called an odd even number checker takes a 4-bit number, so we need to keep this in mind. A, right? 1 to 10 is really very important. Analyzes it and indicates using a 1-bit port, okay, whether the number was odd or even. Okay. The two 1-bit ports are O and E, all right? Odd and even, I guess. This represents, all right, yeah. If a number is analyzed and is found to be odd, then 0 is 1, makes sense, and then E will be 0, all right? On the other hand, if a number is found to be even, is 0, sorry, O is set to be 0, and the even is set to be 1, okay. Show the truth table for the odd even number checker, okay. All right, let's go back on top, straight back on top. A truth table has the inputs and the outputs that we're gonna change. The inputs into the system are 4-bit numbers, and they give you a cap from 1 to 10. Yeah? So like the first thing you need. Everything else will just be outputs. Because they already gave you what the intended output is. Yeah? So I drop the table. So I go to a new page. Alright, so how I just do it, since they say 4 bits, that means I had to start with that, the decrease down. So we can have, as you can say, D0, D1, get D2, and D3. Right, that is your first, that is your input, right? So if you all remember from maths, right, when you're doing the numbers, it does decrease, so it can increase up to where you want. So I had to start 2 to the power 0, 2 to the power 1, 2 to the power 2, and 2 to the power of 3, which is 8. Right, and you just write the numbers in that pattern. So the pattern means first 2 to the power 0, you're inverting every one. So it'll be 1, 2, and you go down the road. Secondly, since they give you a 4-bit number, the maximum amount of patterns they could get will be 2 to the power 4, which is like 16. So that means we have 16 different patterns that you get. Yeah, so there you go. So this one is 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. By what? 4, 8, 12, yeah, 16. Might have to shrink the screen a little bit. Just erase these here, kind of jumble up. 0, 1, 0. All right. So the next one is 2 to the power 1, which is 2. So basically, I include in every 2. So it'd be 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. All right. Third column now is 2 to the power of 2, which is 4. So therefore, I include in every 4. So we go 1, 2, 3, 4. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Right, and then the 3 is 2 to the power 3, so I include in every 8 now. So it'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16. Right, and just like that, I have my inputs. Two things you have to remember, if let's say I have 4-bit, 2 to the power 4 is the maximum amount of patterns for different ways you can write the 0 and 1, as you could see. Right, and then when you're doing that now, after you write the inputs, it just increase. So start from 2 to the power 0 and just go up. And that will give you your intervals. Right, so the next thing we have to write is the outputs. So, yeah, so the outputs for odd or even, so I mean, they're totally that. Right, so now, remember they gave you a criterion on top. Not go to the question. Right, so we just did here and here. We just finished that piece here. All right, it analyzes and indicates using two 1-bit ports what the number was order even. All right, the two 1-bit ports are labeled O and E. Right, this represents odd and even. If a number is analyzed and is found to be odd, it's 0, it's set to be 1. So O is set to be 1 and E is set to be 0. Okay, so that's how you go, right? And I think you all did number systems. What going on, right, is that the basic converting the 4-bit numbers into a decimal number, right? Just to make it simple, right? So that's part column here, and I'll just name it decimal. So this here, if I start from the least significant bit upwards, so this will be least most. So the two, as you said on top, that's converting the binary into decimal, right? That's to make it easier. So you will know what is odd and even. Okay, that's hard looking at this. So this here is 0, clearly. This here, 2 to the power 0 is 1. There is 2. 1 and 1 and 1, 1, 0, 0 is 3. 0, 0, 1 is 4. 5, 6, 7. This is 8. 9, and this is 10. This is 11, 12, 13, 14, and 15. Yeah, because 2 to the power 0 is 1. 2 to the power 1 is 2, so that is 3. 2 to the power 4, so that is 7. And 2 to the power 3, that is 8. 8 plus 7 is 50. Yeah, that's converting the binary into decimal, right? All right, so now we can clearly see what's going on this side. Because we clearly, hopefully, we all know what odd and even numbers are. All right, so I am stopping at this. I don't need to go any further. The reason why is because they clearly said in the question that from 1 to 10. Yeah, so therefore 0 is I don't care. And from 10, sorry, from 11 to 15, I just pattern it with don't cares. Because I don't care something they just don't know. Because they said a specified range of 1 to 10. All right, so therefore this 0 here is I don't care. So you just put X and X. So we don't know what the value is. So I got to say I don't care. Because they specify 1 to 10 specifically. All right, this one here, 1 is a odd. So we have 1 here. And well, it's not even. 2 is even. 3 is odd. 4 is even. 5 is odd. 6 is even. 7 is odd. 8 is even. 9 is odd. 10 is even. And the rest you just padded with don't cares. Okay, you don't know where it is. Wait, you don't care where it is because it's not in the range of what they give you in the question. Yeah, and that is it. You're done. Mm. The hardest part of this probably was just drawing up a table. But for the input parts, if this says a 3-bit input, that'd be 2 to the power 3. So it'd be 8 different patterns. And then from there, just set up the table, increasing to the power 0 to the power 1. In this case, it will end at 2 to the power 2 for a 3-bit number. Draw up your patterns and whatever criterion they give you for your outputs, whether they give you a Boolean expression or whatever, and you get your output values. That is it. In this case, what you had to do to make the question easier is to convert it to decimal, because you know how a decimal number, if it's odd and even, and you just go ahead. So if it's even, it's about 1 in that column, and then the odd will be a 0. Yeah? And that's it. Alright, so nice. So that was this piece there. 8 marks. Vibes. Right. So the second part is say using corner maps, finding meridian, minimum express of P, right, blah blah blah. Okay. Yeah. So same idea. You're drawing up a corner map table. Right? So drawing up a corner map table never gonna change, right? So we know it's a 4-bit number. So 4 by 4 is 6. So you look at the box we had on top. Yeah, so as I say, make sure you know how to draw up that box. Right. So I do the question now. So we know it's a 4 by 4 and we have 4 inputs. So D1, D0, D1, D2, and D3. Right. So I draw up the table quick. So the D0 and D1, D2, and D3. Right. So I'm gonna draw up the columns. So it's 1, 2, 3, 4. And then 1, 2, 3, 4. So like one second thing I like to do is label my number patterns. So 0, 0, right, 0, 1, 1, 1, 10, right? And then now, same thing for the bottom piece, 0, 0, 0, 1, 1, 1, 10. It's nice. So third thing, we need to number the boxes. I mean, do we need to? We don't need to number the boxes for this one because we already know what each bit pattern will give you. So I don't really need to do that. So like for the team, so 0, 0, 0, 0, that was I don't care. Yeah, you just put it in the column up with the answer. So this one here, this is 0, 0, 0, 0, which gave us don't cares. This one could be 1, 0, 0, 0. So 1, 0 for the Z0 and D1. So that'll be here. And then for D2, D3 is 0, 0. So that'll be here and well here. So like, yeah, I don't care. Right here. But well, I don't think that I don't care. That's 0. Yeah. Yeah, so that's how you fill in it. And literally just converting it. So you know it have a split right here. Like the different patterns. So this one here is in the 0, 1 column, and this one in the 0, 0 row. Because how I set it up, the D0, D1 is the horizontal one going across here, which is by default the vertical or the columns. And I set up the D2, D3 piece to be the rows. Yeah. So there's column and row, right? That's looking at each piece as the literally telling you what column it's in, right? So let me just fill it out. All right, so we have 0, 1, 0, 0. That was our 1. This one here was our 1, 0. And this one here is our 0. 1 and our 1, then our 0. Then we have the don't cares here. And then this 0, 1, X, and then a 0. Right? All I did was just convert this table here with the different patterns on this side here into the answer on that side. All right. So the one I did here was for odd, right? Because you had to do 2 tables, basically. You had to do one for odd, and you had to do one for even. So this one here was for the odd. So basically it was this column here. Yeah? Then you had to do one for the even. Okay, you can't put odd and even in the same column map table. Okay, when you could have one output. Yeah? because in the question, they said using Kana maps, plural, important, I read in the question. Find the minimum expression of the output of odd slash even number checker. Right. Looking at this, you can't put odd and even answers in the same Kana map table. That is why they say Kana maps, plural. So you have to draw one for the odd output, which is this, the column here. And then you have to do one for the even output column, which is this one, right? So let's do this one quickly, right? So if you had to get the minimum SOP or the minimum amount of boxes you need to cover all the ones, right? Looking at this, what's the biggest box I could get, right? I have don't cares, so I just gonna treat this don't care as a zero, this one as a zero, and this one as a zero. So I will just get 1, 2, 3, 4, 5, 6, 7, 8. This box in the middle here. So I treat any don't cares in the box here as a 1. Yeah. So, and if I treat anything else on the outside, I will end up getting more boxes now. And I don't need it because I have don't cares. So I could just treat the external ones as zero. When I'm doing this, I just look inwards first with don't cares and then go externally. Try not to like not label all the don't cares as one by default. Yeah. So treat them different. You could have go through the iterations, come and be able to have time in the exam and see which one giving you the best options, right? But as I say, as the more you practice it, as the better you'll get. Right, so the answer for this one for the output. Alright, so the output for odd, same idea was the name. So what common, right? So we know nothing in the D2, D3 common because it constantly changing for the this one here. Different, 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 different. So we know the answer gonna come from on top here. Alright, so looking at this on top here, right, the answer would just be, so you have 1 and 1. So that'll just be D1. Can't be D0 because it's change. Right? And that's for odd. So you repeat the same process for even. So you drop the box. Zero, 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 1, 1, 1, 1, 0. Same thing for the bottom. Then you just plug in the values for it. So x, 0, 0, 1. This one is 1, 0, 0, 1. And you're doing cares. 1, 0, x. So this one here came from the even column, right? Same inputs, but it's a different output. All right, so if I cover in this one here now, looking at it, I could treat these as zeros, and then I'll just end up with the ends combining. Yeah, that's the minimum, one box. So E, or I could write O, you don't change that. So E, what common? So we know nothing common with the part, the D2, D3 part. It constantly changing over. So now the answer gonna come from on top. So what common? We have 0 here, we have 0 here. Yeah, so and this one here not common, okay, change. So therefore this would just be D1 prime. Yeah, that's it. That's all that part was. Right, so that was this one. So now we had to get the, yeah, that was it. Yeah, enough, that's it. 10 marks. Right, using logic gate, implement the odd or even number checker. Okay, so we know the set that is a 4-bit input and a 2-bit output, right? You already have this here. So you just draw a circuit for that. That's the purpose again, minimum SOP. So I'll draw it at the bottom here. So you have D1 coming in, right? And if it odd, D1 is just D1. And if it even, you have the invert. And what logic gate or logic's piece we know that could invert a value, and not gate. Yeah, that is it. Yeah, your D1 coming in. And then if it odd, D1 as you see, just D1. And for even, you invert it. And that is it. Nothing else. Once you break it down, you can try your circuit using your minimum SOP. Yeah, because you're trying to get the simplified circuit. Because obviously, if you had to use the one from on top, your circuit will look a lot uglier. All right. Yeah, and that was question two. All right. So I tried this one. You tried question three. All right. And then I'll try this one next week and you just finish the paper. I know there are work to do, so I won't keep it too long. Okay, for this one, similar idea. I don't know if you all did integrated circuits. So small thing, right? So in this question here, the output of a TTL NOR gate is connected to a number of TTL logic devices. Look, from the time they say that, they want to know what is the minimum amount of TTL devices you need, or the maximum. Depends on which one to choose. If you say minimum or maximum, it's the same working, not going to change, right? It's never going to change. So anyway, so the number of large TTL logic devices with a DC parameter, I input high max is 50, I input low max, right? The I output high max is the I output low max is the V input high minimum is 3.2, V input low max is that. Yeah, the gauge voltage ranges. Nice. So that's something to keep in mind. But that way answers gonna come from. Determine the max. Okay, so in this here he wanted the max number of TTL devices that may be reliably driven by the node. Okay. Alright, so these are the steps. Alright, so there's question three. So the first thing you need to do, right? So you need to calculate the loop state. So you need to calculate the amount of TTL devices for the low state, and then you have to calculate for the high state. Alright, and then from that, you just combine it to get something called the fan out. From this piece here, that's where you're choosing your answer. It's the same thing over and over. Doesn't change. Right, and it has equations for it. Right, so to get the low state, yeah, the symbol for it is NF low, or the number of TTL devices for the low state is just I output low max divided by I input low, right? So this one here, I output low. Talk about the question. I output low was the 10 low. Yeah, that is. Yeah, yeah, that's right. It's max. Yeah, right there, yeah. I don't take too long to look for that. Like this here. So I 10 milliamp. And we have I input low, which is 0.2. What else? I input low. Yeah, right here. Yeah, IO. Right. This one here needs that max. Yeah, nice. So that is the equation. All right, so that'll be 0.2, what it was, milliamps. Yeah. Yes, you see any negative here, that makes sense. But remember, you can't have a negative amount of devices. Say we use the positive value for it, right? Remember, you're trying to get the amount of devices. Say you can't put negative, okay, get negative 10 TTL devices. Can't have negative 10 TTL devices. All right, but anyway, that is the equation to calculate the number for the loop state. I output low max divided by I input low max. All right, and you get that from the table. All right. All right. So the next one, so what that'll be? That'll be 50, I believe. 50 devices. And then the other one is the high state. We call it NF, high shocker. This one is I output high max divided by I inputs high max. Alright, so if you go back to it, I outputs high max. Right, that was where that was. I think it was 500. Yeah, where's that? Yeah, 500 micro. And I inputs max, yeah, 50. Right, so this will cancel with this, and this will cancel with that. 500 divided by 50 is 10. So 10 devices. Right, so we have that. We have this. So we gotta get the fan outs. So let's go min, and that writes the NF low value and the NF high value. So that would just be min 50, comma 10. Yeah. So the maximum you would choose, you obviously choose the minimum, right? So the answer will just be 10. Yeah, so the number of TTL devices that could reliably drive the NAND gate is just 10. You would just choose the smaller amount. Why would you choose the bigger amount? Because the bigger amount is more energy and all that. So if they go to the chalala with the fan out, you just combine the min and the max with the NF1 and NFI, and you just put it together like that, and you choose the minimum. Yeah, and that's, yeah. Okay, you're not going to choose the biggest one, because that wouldn't make any sense. Okay, using more devices when I could just use 10 devices and get the same thing again. Yeah, because, well, on the efficiency. Okay, that was it. Okay, that was that question. 8 marks. So the last one with the knights is this part. Just do that next week, right? So this one here. All right, so a block diagram, CMOS devices, IC2, IC3, for each have an input capacitance of 10 picofarads. IC1 has a power dissipation of 4, estimated 3 wiring capacitance, VDD is 5. Determine the power dissipation due to IC1 when operating at a frequency of 20. Okay, so this question is very short, but you just don't know how to do it. I think I'll just do it on this. Actually, I'll do it on the next one, right? So the only thing I had to do, you just had to calculate the total power dissipation capacitance, which is how an equation fit. You will just go and boil down to memorizing some little bit of equations and then our next equation for the power dissipation, right? So I go to it. So there's 3B, change the color. All right. So they gave you the circuit, right? So the first thing I had to calculate is the total power dissipation capacitance, right? And the equation for that is CPD, capacitance power dissipation, which I gave you in the question, right? Where here. So they said that one here. This is with respect to IC1. Remember, IC1 incorporates IC2, IC3, IC4, and IC5. So they give you the power dissipation for IC1. IC1 power dissipation is due to IC2 to 5. Right? So that is why they said the power dissipation due to IC1. Right? Right. So power dissipation is for IC1 plus the total load capacitance plus the total wiring capacitance, which they gave you already in the question. So they gave you the total wiring capacitance, right? And they gave you the total input. They say each have an input of 10. So you could get the total load capacitance, right? So CPD, if you go back to the question, that is 4, that is the power dissipation due to I1, so 4 picofarads. And then now we need the total load capacitance, right? I said each one have an input capacitance at 10 picofarads, so that is 1, 2, 3, 4. So that is just 4 by this here, because they said each have 10. So it'll be 1, 2, 3, 4, which is 40 picofarads. And then the total wiring capacitance they give me the question already. 3 wiring capacitance, 27 picofarads. Alright, so if you add up all that, you get 71 picofarads, right? And that is the first part. Alright, and then the last thing, which is actually the answer to the ones, the power dissipation is equal to the capacitance, the total power dissipation capacitance, multiplied by the voltage squared, which is VDD, multiplied by the frequency. Alright, so if we go back to the question, VDD is 5 and the operating frequency is 29 megahertz. So therefore this will be 71 picofarads by the 5 squared, and it's at 29 mega, and it just end up with 51.48 milliwatts. Yeah, and that's the question. Very important equation. Yeah, and well, again, very important equation. Yeah, and with that said, we'll pause there for today. We'll finish the next half next week. All right, the next half of the question, it shouldn't take too long. It's just this here, driving the LED question, and then the CMOS, with the pull up and pull down, and that's it. Question will be structured the same way. All right, and so that is it. All right, so any questions, or we all good? I'll see a question. Yeah. All right, nice. All right, so let's pause the recording if no question.